So in this week's lectures, I'm talking about the sun. A few different kinds of things about the sun. A lot of them are applicable to other stars too, but we'll get to that. So, the sun, as I've referred to before, is a very large ball of gas, primarily hydrogen and helium, and it burns, and it shines, it produces energy through nuclear fusion in its core. So I'm going to now talk about the structure of the sun. So here's the sun. This is like a cross-section of the sun. So I can show you the different layers. In the middle we've got the core. This is the real heavy-duty area. The core is a location with such phenomenally large pressures and temperatures that it allows nuclear fusion to occur. Then around the core, the next region of the sun, that was bad, let me just fix this up a little bit. The next region of the sun is called the radiative zone. It's called the radiative zone because the primary method by which energy gets from the bottom of the radiative zone outwards towards the top, towards the outside of the sun, is through radiation. The gas in there gets very hot, it has a lot of energy, and it gets rid of some of that energy by releasing it as radiation, as light. And so the light carries that energy out. Now, technically, the light radiation, right, it could be released in any direction in the radiative zone, but if it goes back towards the core, it doesn't really do anything. That doesn't really cause anything significant to the sun's overall structure to happen. It's only when energy goes outwards that it causes consequential outcomes. So we can think of all the light as radiating outwards and carrying energy outwards in the radiative zone. Outside the radiative zone, is the next layer, which is called the convective zone. Convective comes from the word convection. You may have heard of convection in the context of like a convection oven or something like that. But what is convection? What's the basic process at work here? So, to understand that, you need to understand something about, like, the way gases and fluids work. And you need to understand something about temperature. So temperature, when you get down to it, what temperature is the amount that the particles in something are vibrating. If they're vibrating really quickly, that means that it's hot. And if they're vibrating more slowly, that means that it's cold. The hotter you are, the faster and more energetically your molecules vibrate. And in the case of a hot piece of metal, all those molecules are vibrating really fast, and you touch it and they transfer a bunch of that energy to your atoms, your molecules, and that's how you get burned. But that hot piece of metal, its atoms are still kind of bound to each other, right? So they can shake around, but they're still maintaining their overall shape. Unless you make them so hot that they start to melt, right? Like that's when you start to get like molten metal. But in the case of like a gas or a fluid, the individual molecules and atoms in there maybe are not bound to each other very much. So in that case, the higher the temperature is, that means that the individual atoms or molecules are just flying around at high speeds, right? They're bumping into each other, crashing into each other, all sorts of stuff. They're just moving, right? Instead of just vibrating, they're just moving at high speeds. So that's one important concept. But that ties in with the concept of density. If I were to take a balloon and I put a certain amount of air into it and then I tie it off, it's airtight now. If I were to then start to heat up the balloon in such a way that I'm not popping the balloon itself, I'm just making the balloon hotter, then you would see the balloon start to expand as if I'm blowing it up more. But I'm really not. The truth is that when the molecules inside the balloon get hotter, they start moving around faster. They start bumping into each other and ricocheting off of each other more. And you can kind of imagine how if all of them are moving around faster, that's going to mean that they're going to tend to be further away from each other if they're all moving faster. And so this causes a decrease in density. The molecules, they're the same amount of air molecules, right, because I tied the balloon off, but because of their increased temperature, they're now further away from each other. And that, causes the balloon to expand, because the balloon can do that, and so that decreases the density. So, hot, when it comes to like a fluid or a gas, being hotter causes its density to go down. And conversely, being cooler causes its density to go up. Density also has a lot to do with the way that that floating works, right? If you float in water, or if something floats in water, that's because it's less dense than the water. Something that's more dense than the water will sink. And this doesn't just apply to solid objects. This is why you may have seen oil and water not mixing. The oil just sits on top of the water and doesn't mix in with it. The reason is that the oil is less dense than the water, so it floats on top of the water. So that was kind of a long aside, but it's important to understanding how the convective zone works. So with all that in mind, let's think about the convective zone of the sun. You can imagine that within the convective zone, towards the bottom of the convective zone, the gas down here is going to be hotter, right? It's closer to the core, where all the action is. It's close to the radiative zone, so this stuff down here would be hotter. On the other hand, this stuff up here towards the top of the convective zone would be cooler, right? It's further away from the core, and it's closer to the surface, so it's easier for it to radiate its energy out into space and cool off that way. So the consequence of this, like the composition of the gas is basically the same at the bottom and top of the convective zone. But they have different densities because the convective zone gas at the bottom is hotter. The gas at the top is cooler. So if the gas at the top is cooler, it has a greater density, and the gas at the bottom, being hotter, has a smaller density. And this causes the gas at the bottom to start to float through the cooler gas above it, while the cooler gas above starts to sink down through the less dense gas beneath it. And so this basically causes the gas at the top and the bottom to switch places, like in these little arrows I drew. The hot gas at the bottom floats up, and the cooler gas at the top sinks down. But now that this has happened, you can kind of imagine that now this gas up here that used to be cooler, now that it's down close to the core, it's going to start getting warmed up. And gas at the top, formerly the warm gas, is now further from the core and better able to radiate its energy out into space, so it's going to cool down. And so it's going to happen again, right? It's just a never-ending cycle. It's happening all around in the convective zone. A constant cycle of hot gas at the bottom and cool gas at the top switching places and then, you know, switching roles, and it just happens constantly. That's convection. That's also how convection ovens work, you know, they do it with air. Basically, any kind of convection is just this process in general. And this part of the sun is called the convective zone, because in the convective zone, it's this process of gas of different temperatures moving back and forth that is the primary driver of energy being transferred in this part of the sun. Convection doesn't happen in the radiative zone because of certain details of the way that, like, gases exchange energy and interact with each other. And in the radiative zone, it's basically just too hot and pressurized for convection to happen. So convection can't be used to get energy moved towards the outside of the sun in the radiative zone, but in the convective zone, it totally works. So that's the deal with the convective zone. Next up, we have what is called the photosphere. Excuse me. Now here's the thing. Here I have the photosphere and the convective zone drawn as different things. That's not actually quite right. Technically, the photosphere is part of the convective zone. You know, the convective zone, the convection process goes all the way up to the photosphere, and then all the way back down, right? So this is a little bit inaccurate, and you should recall that the photosphere is a part of the convective zone, but it has its own name because it has some of its own special properties. So we kind of think of them as being different layers, even though really this is just like a special part of the convective zone. But, with that said, the reason the photosphere has its own name is because the photosphere is the portion of the sun that we can actually look at, right? It's called photosphere. Photo, like in photograph, means light. It's the part of the sun that light can actually penetrate through, and so we can look at directly. It's a very thin slice, thinner than I was able. This is not a scale picture, so if this were a more to scale picture, the photosphere would be substantially thinner than I've drawn it here. Because just the sun, there's a lot of stuff going on in the sun, you know. There's all kinds of magnetism, all kinds of gas going all over the place. It's hard for light to get through all that, which is why there's actually a very thin layer where the light can actually reliably get through enough that we can look at it directly. The photosphere is kind of thought of as being the surface of the sun, but since the sun's made of gas, it doesn't really have a definitive surface. So thinking of the photosphere as the surface of the sun is just kind of a convention, but it is a very common convention, and the sun, it kind of looks like it has a surface, you know, and that's roughly what the photosphere is. So it's a pretty good convention, but not quite perfect, if you know what I mean. Now around the photosphere is a much thinner and more diffuse region called the stellar atmosphere. Now the stellar atmosphere has a few different regions to it, but a few different layers of its own. But I'm only going to tell you all about the most well-known and important one, which is the corona. The corona is a very far-reaching and diffuse gas layer of the sun. If you've ever seen a picture of a total solar eclipse where the moon has perfectly blocked the sun and cast a shadow on the earth, then you may have seen that it looks like around the sun with the moon over it, there are like these long, wispy tendrils. That's the corona. The corona actually is quite bright, so we can see it with our naked eye. It's just much less bright than the main part of the sun, so we can usually the main part of the sun just completely drowns it out in light, and so only when we have a solar eclipse can we see the corona. And the corona actually has the really strange property that it's very hot. It's actually a great deal hotter than the photosphere, which is crazy. You know, the photosphere is way denser and it's much closer to the core. So you would expect the photosphere to be hotter, but the corona's hotter. We think the reason this is that the sun has a very powerful magnetic field. This is going to be a recurring theme. The sun's very powerful, dynamic, always changing magnetic field extends out into the corona for sure. And it creates these big loops, these big magnetic field lines that the charged particles in the corona move along. And sometimes two of those field lines will combine into one. And this kind of infuses a bunch of energy into any particles that were moving along those lines when it happened. And so we think that that's why the corona is so much hotter than the photosphere, as counterintuitive as that seems. So yeah, that about covers the structure of the sun. In the next video, I'll be talking about various phenomenon on the sun's surface.